Okay. So my idea for the rest of this afternoon is to present an example and then afterwards discuss a little bit more some other priors, okay? And then for for Wednesday, I have some Matlab codes, and then we can play a little bit with the Matlab codes for this example, which is it's a very simple example, and for another one, which is also very simple, but it's interesting because of the parameters are totally correlated. Okay, so we can play with the priors and examine the effects of the priors and see how we fix this completely correlated parameter here with a prior, and if we don't do it, what exactly happens? Okay, so that's my idea. Okay. Okay, so this example, it's like heat conduction in a semi-infinite medium. It's initially at the uniform temperature T0, and then 4 times larger than 0, we keep this surface at x equals 0 at the 0 temperature. So it's a very simple analytical solution in terms of error function. And then we have 2 parameters here. The parameters are T0 and alpha. And so let's say for this example that T0 is 50 centigrades and alpha is given by this value which corresponds to concrete. Okay, so we think about simultaneous estimation of T0 and alpha. And I'm going to use uniform priors for both T0 and alpha. Okay? And I'm going to start the chain, the Markov chain in the middle of the intervals. Okay? And why I'm doing this? Because when we compute the sensitivity coefficients, okay, with respect to T0 and with respect to alpha, they are linearly independent. Okay, so we have linearly independent parameters. If this is the figure for the sensitivity coefficients, actually for the what we call the reduced the sensitivity coefficient. So I'm multiplying the sensitivity coefficient with respect to T0 by T0, and the sensitivity coefficient with respect to alpha by alpha. Okay, so in these cases, both sensitivity coefficients, they have the units of T, which is temperature, and they can be compared, more easily compared to detect linear dependence and also small magnitudes, because they can be compared to the measured variable. They can be compared to the values of the temperature. Okay? So when we multiply this guy by T0, we get exactly the solution of the problem. Okay? And so this is over here, these curves, they're actually 2 curves. One is the temperature variation, the other one is the sensitivity coefficient with respect to T0. And the red one here is the sensitivity coefficient with respect to alpha. We can see that they have very different forms, so they are not linearly dependent. Okay? Of course, this is a local analysis because I'm examining the sensitivity coefficients for those values of T0 and alpha that I have prescribed here. Okay? So this can be argued, of course, but from the experimental point of view, we can do the sensitivity analysis. Can do the sensitivity analysis for one material, and then we go to the lab, we take the measurements, we estimate the properties, and then we redo the sensitivity analysis. And the same thing would be done, for example, for the design of the optimal experiment, as Professor Lemasson spoke this morning, where you can, for example, maximize the determinant of the information matrix J transpose J. Okay, so and since the sensitivity coefficients, they are linear independent, I'm using priors given in terms of uniform distributions for both T0 and alpha. So for T0, I'm assuming that the uniform distribution is in this interval here between 40 and 65 degrees centigrades. And we have a uniform prior for alpha given by this distribution, uniform distribution between 10 to minus 7, 10 to minus 5 meters squared per second. This can be pretty much argued because T0 is the initial temperature, no? And since we have measurements here, we could use those measurements to get a much better prior, okay? But I'm actually interested here in show you the to show you this the effects of this prior with a very large variance, okay? And same thing for alpha. Same thing for alpha. Alpha, the values of alpha is the thermal diffusivity. The thermal diffusivity of solid materials are more or less between these two values here. So it may be argued from the statistical point of view that this prior is informative because it has finite variance. But on the other hand, from the physical point of view, this is a non-informative prior because any solid material fits inside this interval. Okay?
Alpha is a constant. It's a scalar.
Alpha is a constant, yes. In this example, yes, alpha is a constant. So this is the thermal diffusivity.
T naught is also a constant.
It's a constant because, yes, it's like a uniform temperature at time 0. Okay? But these are the two parameters that appear in our solution, that appear in the formulation of the problem. So they need to be treated as random variables, and as such, for the solution in the Bayesian framework, we have to provide priors for them.
This plate is infinite.
It's semi-infinite. Yeah, see, it's infinite in this direction. It's a one-dimensional problem in this direction here. It's a semi-infinite medium in X here. So I forgot to put the axis here, but the x-axis is here. Okay? Okay, so how does it look? Okay, and I'm using simulated measurements at this position at 10 millimeters below the surface with a standard deviation of 1 degree centigrade. So actually, the experimental data is very noisy. Okay? This is the Markov chain for the thermal diffusivity. Okay? And so this is about 20,000 states. We started the Markov chain at some large value. I'm sorry, this is the thermal diffusivity divided by the exact value. Okay, so this should be 1. So we start the Markov chain at some value over there, and it started coming here, and then we reach some equilibrium distribution. Okay, and this is the same thing, but for the initial temperature. Okay, so we started the chain over here, and it increased the value of the initial temperature, but eventually it came down and actually stayed here around 1. Okay. Of course, with uniform priors, what we are seeing here, okay, is the effect of the likelihood. It's the likelihood that is working here. Okay, and of course, we could consider here also a maximum likelihood estimator that would take into account that the bounds for the parameters. Okay, okay. And but I wanted to show you how the Metropolis-Hastings algorithm behaves. Okay. So of course, these samples which from the time that you start the algorithm, okay, until the chain reach some equilibrium, okay, these samples, they must be neglected, okay, for the computation of the statistics of our problem. So these samples, they are called the burn-in period, okay? So it's while the chains are still heating up, okay? So we neglect these states. Okay? And after we have the chain, after we have the chain either for the diffusivity or for the initial temperature, we can compute the statistics that we want based on the chain values, right? And so we can compute the mean, minimum, the maximum value, the standard deviation, and we can even compute, for example, the uncertainties associated with the mean that is obtained from these samples of the posterior distribution. Okay. But what is the difficulty in this case? We need to get to this chain, right? That's the point. That's the point. We can only compute the statistics of the posterior distribution based on the samples of the Markov chain after we have the chain. And computing the chain, see, in this case, we have 20,000 states. No, in this case, I have like generated the chain up to 20,000 states, yes. But this was a number that I prescribed, no?
If you, instead of using 20,000, you use only 10,000.
For this case, no problem, right?
But you get the same quality in your
Exactly, for this case, yes. For this case, yes. But you only know this after you have computed 20,000, okay? And of course, I could have started with 10,000, you know? And then I realized that, oh, okay, for this case, I only need 10,000.
The suspicion shouldn't tend to 1, the more samples you get.
They are already around 1 here.
Around, that's the possibility.
Yeah, no,
So
but
they
this...
shouldn't diminish the more samples.
Sometimes yes, sometimes no. This is not bad, you know, because you are actually trying to represent your posterior distribution in terms of their samples, or each samples. So it's a statistical distribution. You want to generate actually a statistical distribution. You are not expecting to have one single value, constant value. Okay? And if you have one single constant value, from the statistical point of view, this is very bad because you don't have you cannot represent a statistical distribution with one single value. Okay?
So the distribution you get is with 10,000 samples or 4,000 samples, more or less the same.
More or less the same after I drop off all these burn-in samples here. Yes, yes. But what I mean is that you can only conclude that after you have the samples, no? After you have the samples. And, but you're right, no? And the same thing for here, see, this is a very nice chain actually, because the sensitivity coefficients are linearly independent, and no, so all the conditions are very nice, and so the parameters are not correlated, and you see, this, and from this posterior distribution, we computed the statistics from those samples. We are still going to talk a little bit about how to compute the statistics.
Okay.
But
the samples are obtained after the same amount of time? Or
I'm sorry?
the number of samples, they are obtained after the same amount of time? Or time involved in the process?
No, it's time is involved in the process. It's a transient heat conduction problem. Okay, it's a transient heat conduction problem, but to generate the samples with the Metropolis-Hastings algorithm, we have to compute the posterior and the posterior is the likelihood multiplied by the prior. In this case, no problem, no big deal about the prior because the prior is uniform. So basically what we are seeing here is the likelihood working. And to compute the likelihood, we need to compute the solution of the forward problem. Okay? So to compute each point, each state of the Markov chain, it takes time.
You have to run the full process.
You have to run, exactly.
It's not that you take your samples in different time points. You have to wait the full process.
It's not a sequential process. We are talking, Enrique says, and the other two guys, they are going to talk about this sequential estimation as the solution of a state estimation problem in the course for the filters. But this is not the case. This is actually like it's like a whole domain estimation. Okay, so it's like getting all the measurements and then applying the Markov chain Monte Carlo method. Okay, it's time consuming. It's time consuming. And for this case, this is like this. We are going to run a Matlab example on this very lousy computer, and that costs less than a cellular phone, and we are going to run this like this, okay? And when we run the Matlab code, but the point that I want to make is that you can only decide, okay, how many states I'm going to drop off as the burning period. Have my chains really reached the equilibrium so that I can go ahead and compute statistics out of it that could represent statistics of the posterior distribution? This answer you can only give when you have the chains. Okay? Of course, as you mentioned, see, if I have computed the chain more or less around 10,000 states and drop off like 2,000 states in this case, I would get basically the same thing.
But it's the process. You can use your previous calculations. Once you have computed for 4,000, when you want to compute for 4,000,
oh yes, yeah. No, you don't. But you have to store them. Yes, you're definitely right. No, when if you have the solution of your direct problem is too time consuming, no, you can run this like every 2,000 states and save those 2,000 states so you don't have to, and then you look at those states to decide if they are, they can represent convergence or not. We are going to talk of what do you mean by converging? You know, what do you mean by an equilibrium distribution? And of course, and another very important point here is that how we selected that proposal distribution. Because if we are going to see this when we run the Matlab codes, but if you take steps too large, if these chains were generated with random walk proposals. But if you take a step that is too large, you reduce the chances that the proposal is the candidate point is accepted. And when you reduce the chances that the candidate point is accepted, you might end up with a chain that is like this, with some jumps. And then you might need a very, very long chain to have represented a sufficient number of representative points that can sufficient number of points that can represent your posterior distribution well. Okay? And if you have a very small step, if you have a very small step, a lot of points will be accepted, but this might take very, very, very long to actually come down to the values that represent your posterior distribution and reach equilibrium. Okay? So this is something that you have to test. Okay? And actually there are some empirical rules for this step that you should take in your proposal distribution depending on the number of parameters that you have. Okay. So if we, I'm sorry, this is kind of slow. Okay. So this is the representation of your your samples. Okay. So you see, this is actually the burning period here. You should neglect these guys, and this is your posterior distribution. Okay. Or posterior distribution, which looks like very nicely like quadratics, right? That the contour levels that you would get from a quadratic with an elliptical, with your cross section in terms of ellipses. So because it's actually the likelihood that is working here because you have uniform priors. Okay. Even when we increase the standard deviation to 2 degrees centigrades, so this is what we get for the diffusivity. It's of course now the variance associated with your estimated parameter is large because the uncertainties involved, the uncertainties on your measurements, they are much larger. And same thing for the initial temperature. And when you compare these two, the estimation of both, I have already zoomed in here. The initial states here, they were kind of red dropped out. No? And then we can see here our posterior distribution that looks very nice for this case. Although there appears to be some correlation between the parameters because it's kind of an ellipse here. Now, if we had like a circle, this would be much nicer. And that would actually correspond to a total independence of the two parameters. Okay, so as I mentioned, I would like to run this Matlab code for next time, okay? But before, I would like to finish today with a discussion about two other kinds of priors that are very useful, okay? And most of us, we are already familiar with from the solution of inverse problems with classical approaches. Okay? And these are priors that are called like a Markov random field. Okay? And so these kind of priors that we have seen before, I'm sorry, this is so slow. Okay, so these other kinds of priors, they are very useful when, for example, you have one single parameter, okay? For example, your parameter is like in this case where it's the initial temperature, which is constant, and the thermal diffusivity that is constant, okay? So they are very useful in these situations, okay? But when you have, for example, when your parameter values represent values of a function, for example, a function that varies in time, okay? As we have seen before, something like this, right? So that we have the time intervals. And so this is Pj minus 1, okay? Which correspond to at some time here, Tj. And this is Pj, and then let's say this is Pj plus 1, okay? So in situations like this, when actually the ill-posed character of the inverse problem becomes really apparent, okay? And the regularization is very important to successfully obtain a solution of the inverse problem. We can use priors that are non-informative priors. In other words, these priors, they do not have a finite variance. Of course, we can use, for example, a Gaussian prior. If we know from some other experiment, okay, that our function varies around those values, okay, maybe we can consider like a Gaussian prior around those values here, okay? But many times this is not generally the case. Many times you don't have any information about the parameters, and you know that you need to apply some prior that that can regularize the solution. Okay, and so these kinds of priors, these Markov random fields, they serve very well for situations like this. Okay, so one of them it's called the Gaussian Markov random field. Well, first of all, what is a Markovian random field? When we have a collection of parameters that they only depend on their neighbors, okay, that's what we call the Markov random field. Okay, so this each parameter, they represent the value of a function like here, but they only depend on their neighbors. Okay, the prior for this parameter only depend on their neighbors. Okay. So one prior that resembles Tikhonov's regularization is given in this general form. Okay, where this Antonio that we were discussing during the break. You see, you can represent the prior for the parameters in this form. Okay, where let's say D is some difference matrix and P tilde here is some reference value for P. Okay, for example, D can be like the matrix you use for the first order regularization, Tikhonov's regularization, or for a second order regularization. Okay, so this is for the computation of the first derivatives, and this is for the computation of the second derivative. Okay. All right, but this can be rewritten in this form here. Okay, the prior. Oops. Okay, so the prior there can be rewritten in this form. Okay, so I like the L2 norm here, the square of the L2 norm here. I rewrite this in this form, where then this matrix Z is D transpose D. Okay. If you take a look at this, okay, this looks pretty much like a Gaussian distribution, okay? And for this reason it's called a Gaussian Markov random field, where, okay, if we extend to write in the canonical Gaussian form, okay, the variance for this problem, the covariance matrix for this problem, is given by gamma minus 1, Z minus 1, okay? So this is the form of this Gaussian distribution, okay? But what is the basic difference of this distribution for the Gaussian distribution that we have seen before? Is that Z is singular, okay? Z, D transpose D, okay? This is a singular matrix, which was expected because we are not prescribing any variance for the problem. So the variance here is not finite. So this is an improper distribution, okay? This is an improper distribution. And actually, gamma here, gamma might not be known exactly. Right? Of course, we can play with the values of gamma. We can do numerical experiments to prescribe the value of gamma, but there is a much clever way to do this within the Bayesian framework, as we are going to see in just a minute. Okay, just a minute. But again, no, when we apply, for example, the Metropolis-Hastings algorithm, the fact that this matrix this determinant is 0, it really does not create any problem for us, because we actually have in the Markov, in the Metropolis-Hastings ratio alpha, we have the ratio of the two posteriors, okay? So we don't have to know the denominator. We don't have to know that pi of y, okay? They cancel out when we apply when we compute alpha, okay? For the implementation of the Metropolis-Hastings algorithm. Okay. So this is a smooth prior, okay? And of course, we can take p tilde 0. No problem. Okay? Another prior that it's very important when we have situations that we want to preserve the gradients, differently from this one here, that it tends to smooth out the gradients. But instead of smoothing out the gradients, we might have, for example, a function that is like this. So, oops, I'm sorry. No, okay. We might have a function that is like this, okay? And this is a spatial variation of a function that we know it has some base value here, okay, and some other value in some region here, okay? And what I'm talking about is not the estimation of these two values, but the estimation of the full function. But it's something that we might expect, for example, if inside your domain you have some inclusions, okay? And actually you want to preserve these gradients here, okay? So a very good prior for those situations is the use of a total variation prior, okay? And where the total variation is computed from the variation, from the local variation that, for example, you can have by discretizing this region, okay? By discretizing this region into local values here, okay? So if you are at a point here, at a point ij, okay, you can compute the total variation from the local gradient, okay, in both directions, okay, in both directions. And of course, this can be easily extended for a 3D problem.
What is the notation? I is in nj.
Yeah, the variation, okay. This is the n is the number of neighbors, okay, for this point j, okay.
Oh, I got it. Vj and the sum depends on mj.
Exactly, and all the others, these are the set of neighbors of I. Exactly, yeah. So j is like the neighbors of that point pi, okay. And we can have this parameter gamma here as well, okay. So we have, in these situations, we have two improper priors, so two priors with unbound variance, which serve very well, for example, when we want a smooth solution for the problem, okay? Or when we want to preserve gradients, okay? And both of them, they involve some kind of parameter that multiplies it, okay? And within a very nice thing about this approach within the Bayesian framework is that every parameter that appears in the formulation, even if it is in the prior, and that are not completely known, okay, they can be estimated as part of the solution of course, we need to provide some prior for it. Okay? So we need to provide some prior, for example, for this parameter gamma here. Okay? And for example, we can assume that the prior for this parameter gamma in a Gaussian smooth prior, okay, is given by, for example, a Rayleigh distribution. Okay? It's given by a Rayleigh distribution. So in this case, our posterior, we have the posterior for gamma and for the parameters. And the posterior is going to be given by this expression, okay? Where gamma appears here outside the exponential as well, because it comes, this gamma n plus 2 over 2 comes from this expression and this expression here for the Gaussian prior, Gaussian smoothness prior, and from the Rayleigh distribution for gamma. Okay? So in this case, we only have to prescribe some center value for gamma, which is given by this parameter gamma 0. And when we take samples, when we generate samples, we do not only generate samples for the parameter p with some proposal distribution for p, but we also generate samples from some proposal distribution for gamma. Okay? Of course, this is going to, gamma will be centered around gamma 0, but we are not previously a priori specifying gamma as any parameter, okay? Or by using, for example, the discrepancy principle, okay? In Tikhonov's regularization, we are letting gamma come out of this solution, come out from the solution with this prior. With this prior given, in this case, by Rayleigh distribution. Okay? So this is something that is very nice. And of course, even if you want to have like a Gaussian distribution like this, and you don't know exactly the variance of the Gaussian distribution, or even if you don't know exactly p tilde here, I'm assuming that p tilde is fixed, okay? But if p tilde was not fixed, we could have some p tilde a priori distribution also prescribed for p tilde, okay? Okay. So this is something very nice that that can be used for this case, but this has to be used with caution. Why? Because in the Gaussian smoothness prior, although that we know that this is unbound, okay, we can compute, I mean, analytically, we can get the normalizing constant for this distribution, okay? But for the total variation prior, okay, the normalizing constant for the total variation prior would be obtained by the integration of this expression from minus infinity to plus infinity, okay? And which we don't know. So we don't, and this certainly depends on gamma. What I mean that the constant that appears here in front of it, of the exponential, that depends on gamma, it's not known. Okay? So we cannot apply this approach for the total variation prior, because we don't know the form of this term here. We don't know the we don't know how this normalizing constant looks for the total variation prior. Okay, so actually for the total variation prior, there are some papers that show you how to use some approximation for the total variation in terms of what, like other norms of this difference here. Okay, and for which you can get you can get the normalizing constant that would approximate a total variation prior. But another thing would be simply to do numerical tests. Okay, to do numerical tests to find some. Of course, this would be with these numerical tests, when you fix a value of gamma, your results are marginalized with respect to that parameter. Okay, but this works. Okay, this works. And okay, and what about the output analysis? Okay, so an important point here is that you're not limited to the classical statistical distributions that are very convenient when you are estimating on 1, 2, 3 few parameters. Okay, when you're actually estimating parameters that represent values of a function in some discretized domain, it can be a time domain or it can be like a spatial domain. Okay, you can apply those priors as well. Okay, other priors as well. And what about the output analysis? This is something that you can only do after you have your Markov chain. Okay, so after you have the chain, you can compute any statistics that you want. You can compute the minimum value, the maximum value, the median, the mean, and the variance of your samples. The samples obtained with the Markov chain that should hopefully represent well your posterior distribution. And when the chain is ergodic, okay, the mean based on the values of the Markov chain, okay, they provide a consistent estimate for the expected value of the posterior, okay, which is like the law of the large numbers. But the thing is that like the variance, of course you can compute the variance of your samples. Okay? But what about the variance of this mean value? Okay? The variance of this mean value. So, okay, so if all the samples were independent, the variance of the mean would be the variance of the samples divided by the number of samples that are used for this computation. Of course, this means that you have to reject all the samples before the chain has reached the equilibrium. Okay? So S here is the number of samples after the burn-in period. But this would be the case if all the samples were independent. But actually, since you're generating the samples with this Markov chain by taking those steps, you know, they are always correlated. You know, so actually, you have to divide, instead of dividing by S, you have to divide it by S divided by tau, where tau is this integrated autocorrelation time. Tau is like the number of independent number of samples that you need to skip in the chain in order to get another independent sample. Okay, so this is the meaning of tau. So S divided by tau is like the number of effective independent samples that you have in your chain. No, but you can compute tau. You can compute tau. This is like signal analysis. Okay, you can compute tau by using the autocovariance function of like k, and this is like the covariance when you have the samples there, okay? So the CFF is the covariance at a point R, I'm sorry, C of k, okay? CFF of k is the covariance of the sample at R and with the sample at R plus k, where k is this jump, okay? Is this jump in the Markov chain, okay? It's a number of states in the Markov chain, okay? So you're basically getting the correlation. You're basically getting the correlation when you have the chain there, okay? When you have the chain, you're getting like the correlation of this point with k points ahead, okay? Okay. So you're trying to find the correlation between all the points in the chain, okay? And of course, this should go to 0 somewhere, okay? If these states are uncorrelated, at some point they really become uncorrelated, this should go to 0. Okay? And you can also compute this, instead of computing the autocovariance, you compute the normalized autocovariance, which is the autocovariance divided by the covariance for k equals 0, and the covariance for k equals 0 is actually the variance, because it's the covariance of R with respect to P at state R with respect to P at state R. Okay. And this is 1, and then this is expected to go down to 0 as k increases. Okay. And the autocovariance, the integrated autocorrelation time, is related to this normalized autocovariance function by this formula, okay? By this formula. And computing this, you can, there, for example, in Matlab, there are functions to compute rho, okay? And when you compute rho, actually, you see that it starts with 1, and it goes down to 0, and then it oscillates around 0 because of the random character of the stochastic character of the Markov chain. Okay, so actually you do not need to sum it up to infinity. Okay, you have to sum it up until it becomes 0, and because afterwards this is only noise. Okay, this is only noise. So in this case, then you can compute an estimate for tau. Of course, this is an estimate for tau, and with an estimate for tau, you can compute the variance of your mean value. Okay, so and that's what you do, you know. And the interesting thing here is that you can prove that your mean has a Gaussian distribution. Okay, so it's like the central limit theorem. Okay, so your mean has a Gaussian distribution, but not your Markov chain. Okay, not your Markov chain. You don't know which distribution you can get from the samples of your Markov chain. Okay, but the mean, it's expected to be Gaussian. It's expected to be Gaussian. Okay, so you can compute, okay, the mean from the samples, from your samples of the Markov chain, okay, the variance of the samples of the Markov chain, and then the variance of the mean. Okay, the variance of the mean. So this is nice. This is nice because you can represent your mean with its associated uncertainties. Okay, so you can get the uncertainties from your posterior distribution that you you have the variance of your posterior distribution, which is represented by the variance of the samples generated with the Metropolis-Hastings algorithm for your Markov chain. But you can also represent the mean value that you can get from all those samples with its associated uncertainty. Okay, like this, right? Like for a 99% confidence interval, C here is 2.576. Okay, and these are different ways of representing your statistics. Okay, your statistics. And finally, for today, you can check the convergence of the Markov chain by different ways. We are going to see, for example, you can plot the logarithm of the posterior. And you expect that the logarithm of the posterior, it converges, okay? And so you know more or less how many states are associated with the burn-in period, and you have to drop those states for the computation of the statistics of the samples, which in turn, in other words, mean the statistics of your posterior distribution computed through the samples, okay? But there is this very simple way to check convergence of the Markov chain, okay? When, for example, when you drop some initial states and you compute the mean at the beginning of the chain and the mean at the end of the chain, okay? And then you compare these two means, and this difference is expected to be to 10 to 0, okay? To 10 to 0. And of course, it's nice. It's a good practice to repeat the chains for different initial states, so that at least you know this is an ergodic chain. And but there is a method to generate multiple chains, and this from this reference here. Okay, and then you can make inference from these multiple chains. Okay, so you can, for example, start with different computers with different chains, and then at the end you get some converged chain from these multiple chains. Okay, to make the statistics out of it. Okay, so I would like to stop here today, and then we don't have class tomorrow, and on Wednesday we restart by looking at the Matlab codes, okay? Because then we are going to see, for example, the effects of the proposal, and we are going to see also how to compute these means and these covariances, everything. Okay? So, any questions, comments? Anything? No? Okay, so thank you, and see you on Wednesday. Okay, thank you. Actually, see you tomorrow morning, but for Lemação's class. Thank you.